Hey Sapil, and welcome back to today's LiveWork, where today we're going to be talking about multivariable calculus, specifically on triple integrals, surface integrals, and also line integrals. So without further ado, let's just get things going, shall we? So yeah, in here we got six problems. No, we got five problems, and yeah, well, within these five problems, we are going to be talking about each of them and also their applications and also some theorem as well. Let's just get started. Let's say we be the portion of the cylinder x squared plus y squared is less than equal to 1, lying in the first octant. X is bigger than 0, y is bigger than 0, z is bigger than 0, and below the plane z equals to 1. Set up a triple integral in cylindrical coordinates which gives the moment of inertia of C about the z-axis. Assume the density to be 1. Give the integrand and limits of integration, but do not evaluate. Okay, so yeah, in here we are going to be trying to figure out what is the moment of inertia about the z-axis. So yeah, basically you want to try to find the distance first, which is gonna be something. But yeah, let's just let's you know what? Let's just actually go ahead and just straight away write the entire thing straight away. Let's just reduce the size first. Um, okay. Um, okay. So yeah, in here, yep, we have nope, command shift Z, command shift Z. Okay. Okay, so yeah, the first thing is that we want to start with the triple integral of C, and then the distance from the origin to the point. No, actually it's not from the origin. It is like from it is it is from the z-axis, which in this case it would be z equals, no, sorry, the radius would be the square root of x squared plus y squared, as that's the distance between a point to the z-axis. But then yeah, obviously the radius you need to square it. So you will just eventually get yourself x squared plus y squared. And then in here you would have the dv, which is basically the volume. And so if you want to actually to turn this into cylindrical coordinates, um, so yeah, basically cylindrical coordinates is like polar coordinates, but you add in a z-axis. So yeah, with that you could actually just straight away and write this guy down. So like yeah, the first thing that I'm gonna be doing is to just to put in the theta. Well, like yeah, the theta in here would be, let's just let's just draw the first octant first here. There you go. There you go. And this is the cylinder. And yeah, this guy here is actually from 0 to pi over 2, as that's the limits of integration for the theta. And now, second thing, let's go ahead and just do for the radius. In this case, it is simply from 0 to 1, because that's the furthest point that you could get from the z-axis. And then after that, you want to do the last integral, which is basically going to be covering the z-axis, which in this case it's going to be from 0 to 1. In here we want to transform x and y into cylindrical coordinates, which would mean that x would be r cosine theta and y would be r sine theta. But then yeah, this will going to be r squared. But then now we want to convert this dv into dz, dr, and d theta, and that means that you need to multiply this again by r, dr, no, dz, dr, d theta, dz, dr, d theta. Therefore, we actually, and yeah, by the way, in here we got the density to be 1, so like, yeah, it is just basically just multiplying it by 1 again, but yeah, we just, we just, we just ignore it straight away. So yeah, in here, this would be, let, oh, let me just copy paste this. So yep, this one here. Let's copy this, and then let's paste it downwards there. Mm-hmm. But then yeah, this guy here turns into AR cubed instead. And yeah, you could actually just evaluate this, but yeah, obviously I'm not gonna be doing that because the problem doesn't actually tell me to do so. So yeah, that's the first problem. Okay. Okay, let's go with problem 2. A solid sphere of radius a is placed above the xy plane, so it is tangent at the origin and its diameter lies along the z-axis. Give its equation in spherical coordinates. Okay, so like yeah, you want to have a solid sphere as of radius a. Okay, it is placed above the xy plane, so it is tangent at the origin, and its diameter lies along the z-axis. Okay, so when you just start imagining this thing here, so like yeah, you could have like a ball, and then you just take a z-axis, and then you have a plane which is just light until it hits the ball, which is perpendicular to this line. So like yeah, let me just sketch this like that, as this thing here would be the ball, just like so. That's my best at drawing this ball. So like yeah, that is the case. So yeah, basically the way for you to actually to make a sphere, you need to know about the centers first, which in this case, the center would be at x equals to 0, y equals to 0, and then z at a. It has to be at a because like you want to make this guy in tangent with the xy plane. And in order for that to work, you want to make sure that yeah, your z-axis, no, sorry, the center of the sphere must be at 0.0.8. That's something that you must know. And this must equal to a squared. Okay, and so now we want to actually to go ahead and just open this up. You can just do this pretty easily. X squared plus y squared plus z squared minus 2z a equals to 0. Okay. Okay. So now if you want to try to figure out what is this equation is going to be, well yeah, first thing first is that x squared plus y squared plus z squared is going to be rho squared. That is something that we know. And yeah, basically rho here is basically the distance from the origin. Okay? Sorry. So okay, so like yeah, and here x squared plus y squared plus z squared here is going to be rho squared. But then what is z? So like yeah, basically if you know about the so basically if you want to know about this, if you want to know the specifics, x is x is gonna be cosine theta sine psi sine psi. Y is rho sine theta sine psi psi. Z is cosine psi, which is which is going to be the one that I'm going to be writing. Two row a sine psi sine psi sine no cosine sorry my bad cosine psi. Okay, this would equal to 0, and this is basically one of the equation. But obviously, when you just do this entire thing and then you just actually just analyze that, yeah, you know that rho equals to 0, and then you have rho minus 2a cosine psi, which is also another value, which is so like yeah, you could just basically state this as 2a cosine psi, just like so. As this thing is gonna be fulfilling that, yeah, what happens when rho is 0, you could just crack that out and figure out what psi is. Yeah, that's that. Well, actually, what happens when rho equals to 0? What is psi? Ah, yeah. Psi is pi over 2 or negative pi over 2, which basically makes sense in here. Because like yeah, the psi here never goes into the negative value. So like yeah, that's that. Okay, give the equation of the horizontal plane z equals wait yeah z equals to a in spherical coordinates. Okay, so how would you basically write z equals to a in spherical coordinates? Well, basically you have already figured out that yeah, z is rho cosine psi. So basically you know that rho cosine psi equals to a. Therefore you know what a is. A equals to a second psi. See, it is pretty simple. Okay. So yeah, this is part B. This is part A. Okay. Set up a triple integral in spherical coordinates which give the volume of the portion of the sphere as lying above the z equals to a. So basically z equals to a is there. Okay, give integrand and limits of integration but do not evaluate. Okay. So we first need to figure out where is the final spots. Like yeah, I don't think like yeah that's the real word, but yeah. Oh well. But yeah, we want to figure out when would these two functions actually be the same? Well, obviously you got the rows which you can use. So like yeah, I'm gonna be putting the same rows together. So like yeah, this guy and this guy, I would just make it into an equation which you would actually get 2 cosine psi equals to second psi. Yep. And so when you just do the entire evaluation, you would get cosine squared psi equals to half. Yep, that should be the case. Cosine squared psi is half. And so when you just try to crack this out, cosine psi is plus minus square root 2 over 2, which is two different values. One of them is pi over 4, the other one is something else. But we know about one thing is that, yeah, the psi can never be more. Or like yeah, you could actually just see from the picture that yeah, the psi here couldn't be more than pi over 2. Instead, pi over 2 is the maximum. So we figured out that yeah, psi must to be pi over 4, as that's one of the limits that we have. So when we just actually just go ahead and just solve this third thing, um, first thing is that we can just figure out theta straight away. We c- we can figure out the limits of theta because like yeah, this thing here revolves fully. So like yeah, we know that it's gonna be from 0 to 2 pi. Yep. And then after that, we want to go ahead and just figure out what psi is, and and yeah, in this case we have figured it out. But yeah, where do we actually start? We actually start when psi equals to 0 because like yeah, it is literally vertically up there. So we will be starting from 0 all the way to this limit that we got, which is at equals to pi over 4. And that is where it is actually touching, like yeah, the plane is touching the sphere. So that's that. And then after that we want to go ahead and just figure out the last one, which is the rows. But yeah, when you just change the psi, the row would the row would the row would absolutely change. But yeah, we can actually just plot it in, and we know that actually um, the plane is gonna be below this sphere because like yeah, basically from the text we got that information. So you could write this guy as a second psi, and at the top there would be 2a cosine psi, and that's the answer. Good. Okay, so now when we have figured this out, we want to figure something out, which is the integrand. And yeah, in this case, the integrand is not 1. 1 would be true if it is dv, but we know that, but we just transform this dv into d rho, d psi, d theta. So we need to figure out what is the integrand, luckily it has been done, and it will actually turn out to be rho squared sine psi. That is the integrand. But then yeah, don't forget to write in the all of the d somethings. Like yeah, in here it's d rho, d psi, d theta. And there you go. That's your answer for part C. Okay, pretty good. Um okay, let's go for problem 3. Let f vector equals to 2xy plus z cubed plus x squared plus 2yz plus y squared plus 3xz squared minus 1k hat. Show that f vector is conservative. Now, when we actually just do something about conservatives, um, this, or like yeah, you need to know about this thing is that yeah, the curl is gonna be 0, but instead of you trying to figure out what the curl is, instead you could just do this instead. First, you just go ahead and just write p, q, and r, just like so, and then you could just do this guy instead, p, Q, and R. Okay. And so now we want to write from here would be X, Y, Z. In here, this would be X, Y, Z. So yeah, we want to make sure that these partial derivatives are the same. And yeah, by the way, this thing here is P, this thing here is Q, and this thing here is going to be R. Okay, let's go ahead and just first do PZ first. So yeah, when you do PZ, it is going to be 3z squared at the very end. What about Rx? When you just do the partial derivatives, like yeah, y is constant, -1 is also a constant. That means that yeah, 3z squared is gonna be the answer. Okay. What about qx and py? Let's see. Let's see what happens when you just take the partial derivative of q in terms of x. That would be 2x. What about py? Py, that would be the same thing. It's 2x. And lastly, for ry, when you just do it, it's going to be 2y and 2y. And so we figured out that yeah, this entire thing here is conservative, which means that you could have a function. So yeah, basically f vector is the gradient of a function. But then now for part B, it is asking you to find what is this function. Well, yeah, for me, the easiest way is to do the entire thing straight away. What do you mean? So this is how I actually do it. So you first actually do p. So yeah, you first actually just go ahead and just do integrate p in terms of x straight away. Inside your mind, it would be x squared y plus xz cubed. And obviously you have the plus c of something else. And now when you actually just do the integral of q in terms of y, you would get x squared y, which is something that we already have, plus y squared z. And that's that. But then, like, yeah, last time we don't actually figured out what xz cubed is. But yeah, we have actually at least figured this out. Okay. And now lastly for the r, we want to go ahead and just do the partial derivative of r in terms of z, which is going to be zy squared, something that we already have done, xz cubed, something we have already done, minus z, which is something that we haven't done, plus an arbitrary constant, because we have already finished out the entire thing. And so you could actually just check this out using your gradient stuff. Oh yeah, by the way, it it states to show your work even if you can do it mentally. Ah, so yeah, that's basically how I do it. But yeah, the best way to do it is to just actually to state it like this, okay? Well, like yeah, there is like multiple steps, but yeah. Um, you first try to find what f is. This is like your first attempt, which would be x squared y plus xz cubed, okay? Plus a constant, which is a function of y and z. And so now when you take the partial derivative in here, in terms of y, it's going to be 2x. It's going to be x squared. Xz cubed is going to be is going to go missing. g derivative of y point z. Well, actually, it's not g derivative, but yeah, it's gy of yz. But then we know about what this gy y of z is. G of no gy of y is y and z. It's gonna be 2yz, some which is from here. So when you just figure this out, you want to crack out what g is now. So when you just do the entire thing, you would figure out this going to be y squared z plus another constant, but in terms of z. And so when you just do the same derivative, like when you do the same partial derivative, but in terms of z, it's gonna be 3xz squared plus y squared from here plus hz. And in this case, in this case, we just figured this out to be 1, -1. Therefore, I know what hz is. It's gonna be a minus z plus a constant, which is the answer. So that's how I actually write this starting down. But yeah, this is not really a fully founded one. Well, okay. So yeah, let's go to the next problem. Okay. The next problem is here. Problem 4. Let S be the surface formed by the part of the paraboloid z equals to 1 minus x squared minus y squared lying above the xy plane, and let f vector equals to x plus y plus 2 1 minus zk hat. Calculate the flux of f vector across S taking upward direction as the one for which the flux is positive. Do this in two ways: by directly calculating the surface integral of f vector dot n ds, or b by computing the flux of f vector across a simpler surface using the divergence theorem. Okay. Oh, we want to go ahead and just figure this out. Okay. So we got here a z equals to 1 minus x squared minus y squared. Okay. In order to solve this, the easiest way for you to do this is to actually the first thing is that you want to know what is n hat ds in here. And yeah, luckily in here we already got the function that that means that you can actually just figure out what is n hat ds is. It is gonna be the plus or minus, but yeah, in this case it's plus because it's the upward direction. So it's n vector ds of the vector take the partial derivative of z in terms of x. That will be negative 2x, but then yeah, you just need to switch up the signs. That means it's 2x. Point the partial derivative of z in terms of y, but then yeah, you obviously take a negative at the front as well, which is 2y point 1 dx dy. That's basically n vector ds. And so now when you just go ahead and just plug in the numbers, it's gonna be chaos. So okay, you just plug in the double integral of the surface of so you want to take the dot product of f vector with this n vector ds. So when you just take the dot product, that would be 2x squared a y times 2y, that's 2y squared, so it's plus 2y squared, and then plus 2 1 minus z, plus 2, and yeah, in here 1 minus z you want to replace it by the z that you gain, which is the 1 minus x squared minus y squared, which is x squared plus y squared, dx dy. Okay, so when you just figure this out, you would get this double integral of the surface of 4x squared plus y squared. Yeah, 4 of x squared plus y squared dx dy. And in here, the surface here is actually going to be the circle. Because it is lying above the xy plane, that means that z is 0, okay? So if it's lying above the xy plane, that means z equals to 0. That's basically that is the limit. And what is the surface you get? It is a unit circle, and that's it. And so you're just basically trying to be finding what this guy is. So when you just put this guy in, and this guy here is a unit surface, um, you would get in here would be 0 to 2 pi. Same thing down there, it's from 0 to 1, and then it's gonna be r cubed. It is basically some double integral stuffs, dr d theta. And so when you just compute this, you would get r cubed over 4, which is going to be 1 when you just evaluated it. And then you just plug in 2 pi. It's going to be 2 pi. That's the answer. But then there is another way, which is by using the divergence theorem, which is stated that basically when you have this guy to be a closed surface, you could do that. You could use the divergence theorem. So when you take both of the surface, but yeah, obviously this thing needs to point outwards. So when you just take this guy here, S1 plus S2, yeah, this thing here must be a closed surface. Sorry about that. Of f vector and hat ds. This would equal to, when you just do the thing, you would get the divergence theorem to be the triple integral of the surface, no, of the solid by with the integrand of the divergence of f vector dv. So this thing here is a. And so how would you actually compute this? Okay. So yeah, basically in here the divergence of f must to point away from the object. So that means like, yeah, in here, so like, yeah, in here we could actually just separate this thing into these two things, which is the s that we want to find of f vector n hat ds, and then we want to add this by, in here n hat must go negative because it needs to point out, because it needs to point outward. And yeah, by the way, when you just do f vector n ds, it is going to be automatically pointing outwards, because you know about these things. Because like, yeah, you could just model the entire thing straight inside your mind. Yeah, I know. I know. Not everyone can do that. But yeah, I know for certain that, yeah, that same thing is going to be the same for the one that you just get at the top. And so you want to add this up by the surface underneath there, which is going to be a unit circle. I am just going to be labeling that as O, or S2 you could call it. And yeah, in here the n hat direction would be pointing downwards, or 0, 0, negative 1. Which means that the surface in here would be z minus 1. But I know what z is. Z is 0, so that means that this is negative 1 of ds. That's a very quick way for you to compute this thing, I know. And then, what is the divergence of f vector? When you just do the entire computation, in here the divergence is going to be, you want to take the partial derivative of x, and then, so yeah, you just basically take the partial derivative of, so like, yeah, in the I hat it will be partial derivative of x. If it's j hat, it's partial derivative of y. If it's k hat, it's the partial derivative of z. It's pretty simple. And so what you get is actually a 1 plus 1 minus 2 dv. And this would actually result into 0. 0, and then this guy here, it is basically stating the negative area. So that means that this starting would result to 2 pi. That's the double integral of sf vector n hat ds. And that's the answer. See? It is pretty simple once you know about the technique. Okay. Let's do problem 5. Let f vector equals to 2xz. Sorry about that. I hat plus y squared k hat. Calculate curl f vector. So, to compute curl, you just need to take the del cross the f vector. And yeah, what's del? Del is something that you couldn't really actually explain this because it is not a true vector. It is just a partial derivative. So when you just basically do the starting, so when you take a cross product, it's I hat j hat k hat. I hat j hat k hat. Of this guy here is gonna be del over x over del x. No, sorry, it's not del. It's d over dy. I normally call it as partial d. And in here it's gonna be the vector that you have minus 2 xz, and that's y squared. And so you want to compute the determinant of this entire thing, which is totally not numbers, but yeah. So you first actually go ahead and just compute what is the value of the I hat, which in this case, when you just cross it, it's the partial derivative of y squared over y. That means that it's going to be 2y. Subtract that by the partial derivative of partial derivative of 0 in terms of z, that's 0. So that means that it's only 2y I hat. Subtract this by the partial derivative of 0 in terms of x, that's 0, and then the partial derivative of minus 2xz in terms of y, that's also 0. So it's minus j hat. Very good. We don't have anything in terms of j hat. Wait, no. No. Whoops. Yep. I think I just actually compute the one for the k hat, which is going to be true. For k hat it's going to be 0. We got that. But then what's for j hat? It's gonna be the partial derivative of y squared. That's 0. But what happens when you take the partial derivative of negative 2xz in terms of z? It's gonna be negative 2x. So in fact, this thing is gonna be 2x j hat. Just like so. And then lastly, for the k hat, it's 0 because we have already computed that. Yes. Okay. So this is the curl of f vector. And so now part B. Show that the surface integral of curl f is 0 for any portion r of the unit sphere x squared plus y squared plus z squared is 1. For any finite portion. Take the normal vector pointing outwards. Okay. So, okay, first thing that you need to know is that, like, yeah. Like, yeah. The f vector is going to be pointing outwards, so we know about that. Wait, what? What? Wait, no. 2x1 plus 2xy, no. Something's not adding up. Yeah, something is not really adding up. Because the curl f vector dot n hat ds, but n hat I know it's 1, 0, 0. Wait, no, it's x, y, z. So it's 2xy plus 4xy. Like, yeah, pointing outward, it doesn't make sense. Show that for any finite, as long as it's finite, it's fine. But I need to make sure that this finite region must be 0. That means that curl f vector dot n hat must be 0. Okay. This is gonna be interesting. Although I doubt that, yeah, this guy here is actually that. Instead, it might be something else. It might be. Like, yeah. When you just basically, try to figure this starting out, like, yeah, the del cross f vector would just give you this value. Like, yeah, I know it's gonna be 2y in the I hat direction. For the j direction, it would be, you take that. Like, yeah, this sign here should actually be a negative. Yeah. Because like, yeah, it's a negative, and then you just take another negative, and then you just take another negative. Because that's the meaning of determinant. So like, yeah, when you just take del cross f vector dot the n hat, which in this case here to be x, y, z for the n hat, because like, yeah, it's a sphere. That means that this guy would equal to 0, which is basically the integral of the surface integral of 0 is 0. Okay. Part C, as this is the final problem. Okay. And this is the most easiest one. Show that the line integral of a closed loop of f vector dot dr vector is 0 for any simple closed curve. C on the unit sphere x squared plus y squared plus z squared is 1. This is a very easy thing. Why? Because any finite portion R of the unit sphere is gonna be definitely be, well, yeah, it's not definitely, but there is a finite portion of R that you could actually trace using only one line, and that one line would actually basically tell the entire thing. And yeah, this thing here could be proven by Stokes' theorem. By Stokes, it's gonna be true. So like yeah, I don't really need to compute the entire thing because I know about Stokes' theorem. So when you just go ahead and just try to figure it out, like yeah, Stokes' theorem basically states that yeah, this guy here can be converted into this guy. That's basically the short story. But yeah, I guess that's all. So yeah, thank you very much for you guys who have actually stick around to see this live work. And yeah, we will actually gonna be meeting you guys on the next live work. So yeah, see you guys later. Goodbye.